Dear students, another model which we consider is Lin-Log model. Lin-Log model. Unlike in the log-lin model, we consider the independent variable in log form. That is, we measure what is known as absolute change in y for a given proportionate change in x. In the Lin-Log model, our concern is to estimate absolute change in y for a given proportionate or percentage change in x. Such models are known as Lin-Log models. The model can be written as yi samam beta 1 plus beta 2 ln xi plus ui plus ui. Now, the slope coefficient beta 2 is equal to delta ln x by delta y. Delta ln x by delta y. That is equal to y is equal to beta 1 plus beta 2 ln x plus u, and beta 2 measures delta y by delta ln x. That is absolute change in y for a given proportionate change in x, delta y by delta ln x, or a delta y by delta x by x. Beta 2 is equal to delta y by delta x by x. Can also be written as delta y by delta x into x by 1. Okay. Delta y by delta x into x. Delta y by delta x into x, or delta y divided by delta x by x, that is delta y by x by delta x, or delta y by delta x into x by 1. That is beta 2, and that is beta 2, that is delta y by, that is dy by dx, dy by d ln x. Now, what is the slope of this model? Slope is delta y by delta x, delta y by delta x. So, slope can be written as beta 2 into 1 by x into 1 by x. X and x will cancel, delta y by delta x. So, beta 2 into 1 by x in the Lin-Log model. Slope is beta 2 into 1 by x. And what is elasticity? Elasticity is delta y by delta x into x by y. So, beta 2 into 1 by y. Beta 2 into 1 by y is elasticity. Beta 2 into 1 by y is elasticity. Beta 2 into 1 by x is slope. Now, this equation states that absolute change in y is equal to slope times absolute change in beta 2. This can also be written as delta y is equal to, from this, beta 2 into delta ln x. So absolute change in y is equal to beta 2 times relative change in x. If multiplied by hundreds, it will give you absolute change in y for percentage change in x. As an example, if delta x by x is 0.01 or 1%, 0.01 or 1%, then absolute change in y is delta y can be written as 0.01 into beta 2. Beta 2. Because if the 1% change in y causes beta 2 times into 1% change in y. As an example, if beta 2 is equal to 500, delta y is equal to 0.01 into 500 equal to 5. Equal to 5. The interpretation is that if there is a 1% change in x, absolute change in y is 5. So, it is very important to remember that once this model is estimated, multiply the slope beta 2 with the 0.01. Otherwise, interpretation will be misleading. So, once the model is estimated, always multiply beta 2 with the 0.01 to get change in y. This is important to be remembered. And this model gives absolute change in y for a given proportionate change in x. Beta 2 is change in y divided by change in, or absolute change in y divided by proportionate change in x, or percentage change in x. And slope is beta 2 into 1 by x. Elasticity is beta 2 into 1 by y. And delta y is equal to beta 2 into delta ln x, or delta x is, if delta x is 1% or 0.01, delta y is 0.01 into beta. So, if the value of beta 2 is given, multiply, if beta 2 is, so for example 500, multiply this with the point, whatever is the value of beta 2, multiply this with the 0.01, then only you will get a delta 1. Now, as you can see in this model, the slope is beta 2 into 1 by x. Beta 2 into 1 by x. So naturally, as x increases, the slope decreases. So we have a pattern like this. This is y, this is x. If beta 2 is positive, you have a pattern like this. When x increases, y increases but at a diminishing rate. That is, slope decreases as x increases. If beta 2 is less than 0, again it is negative, but the negative slope decreases in absolute terms. So, if this is the model, the Lin-Log model, the slope is beta 2 into 1 by x, elasticity is beta 2 into 1 by y, and the pattern is something like this. The message is, if you have y on x, and if you plot this data, and if you observe patterns like this, you experiment with the different patterns. Now the question is, what is the application of a model like this? A celebrated application is the Engel what to say, the Engel's law of consumption, which says that as income increases, the proportion of income allotted for food decreases. So, if your model is food expenditure is equal to beta 1 plus beta 2, beta 1 plus beta 2, income ln income plus u. Because if you plot the relation between food expenditure and income, as you will see, as income increases, food expenditure increases at a diminishing rate. The pattern will be like this. As income increases, expenditure on food increases, but at a diminishing rate. And as you know, the slope decreases. If beta 2 is positive, beta 2 into 1 by x, slope is positive, but the positive slope decreases. If it is less than 0, in absolute terms, beta 2 decreases. The celebrated application is Engel's elasticity function or Engel's law of consumption. As an example to this Lin-Log model. Lin-Log model. Remember this pattern. Now, a fourth model we consider is reciprocal model. Reciprocal model. A fourth model we consider is the reciprocal model. Now, suppose that we have a model like this. yi summum beta 1 plus beta 2 1 by xi plus ui. This is the example of reciprocal model. And as you can see, this is a model which is non-linear in x because x appears as 1 by x, not as x, but it is linear in parameters. So you can estimate this model. If you have data on y and x, your dependent variable is y, the independent variable is 1 by x. You regress y on x, you will get estimates beta 1 and beta 2. As beta 1 and beta 2 appears as linear, you can estimate this model using OLS. The only thing is x appears in this model reciprocally. Now, let us see what is the feature of this model. As you can see, as x increases indefinitely, beta 2 into 1 by x, beta 2 into 1 by x, this term. As x increases indefinitely, the term beta 2 into 1 by x approaches 0, and naturally y approaches the value beta 1, which is known as the asymptotic value. The asymptotic value beta 1. As x increases indefinitely, y approaches the asymptotic value beta 1. So there is built in such models is an asymptotic or limit value of beta 1. Built into such models is an asymptotic value or limit value of y, that is beta 1. And let us see some of the possible shapes. Now, y, x and 0. This is beta 1. Suppose that beta 1 is greater than 0, beta 2 is also greater than 0. If beta 1 is greater than 0, beta 2 is also greater than 0, as x increases indefinitely, y approaches the asymptotic value beta 1 and beta 1 is positive in this case. The second possibility is y x 0. Suppose that beta 2, this is beta 1, beta 2 is positive, beta 1 is negative. So as x increases indefinitely, again y approaches the limit, the asymptotic value beta 1, but now beta 1 is negative. Beta 1 is negative. These are two possible shapes of reciprocal models. If both are positive, and remember this, if beta 2 is positive, the curve decreases throughout. The curve depicting the relationship between y and x decreases throughout. To see this, we have to see the slope. Now this yi is equal to beta 1 plus beta 2 1 by x can be written as x raised to minus 1 plus ui. Now what is the slope? The slope delta y by delta x or dy by dx is minus beta 2 into 1 by x square. Minus beta 2 into 1 by x square. So slope is minus beta 2 into 1 by x square. Differentiating this, minus 1 beta 2 xi raised to minus 1 minus 2 1 by x square. So minus beta 2 1 by x square. So the slope is negative throughout if beta 2 is positive. Now beta 2 is positive, slope is negative throughout. And if beta 2 is negative, then you will get positive slope throughout, because if it is negative, minus into minus, then beta 2 1 by x square. So this is the slope for the reciprocal models. Reciprocal models. Now what is the elasticity? Now elasticity can be written as minus beta 2 into 1 by xy minus beta 2 into 1 by xy minus beta 2 into 1 by xy. Elasticity is delta y by delta x. Delta y by delta x into x by y. That is elasticity. Delta y by delta x is minus beta 2 into 1 by x square into x by y. As you can see, it is minus beta 2 into 1 by xy, x square by x, xy. So minus beta 2 into 1 by xy. This is the example of a reciprocal model. And remember this, one celebrated application of reciprocal model is the Phillips curve in macroeconomics. The point is, if x increases indefinitely, there is a limit value to y. Can be used in various contexts, and we will consider application of these type of models when we consider the multiple linear regression model. Multiple linear regression model. Now, in addition to these models, we can also consider various powers of x, say x square, x cube, etc., to estimate quadratic functions, cubic functions, and the like. Such models will be discussed in the context of multiple linear regression model. That is in the next section. Now, one more point regarding this log-log model. Let me consider a few more functional forms, just to clarify a few more points. If both the y and x are in log form, suppose that y is this, x is this, then this is a possible shape if beta 2 greater than 1. If beta 2 is greater than 1. If beta 2 is less than 1 and greater than 0, this is a possible shape. Then consider this y, x. Now, it is possible that we can have many functional forms like this. All these are estimates of elasticities with say beta 2 less than minus 1, beta 2 equal to minus 1, or beta 2 greater than minus 1, less than 0, etc. These are all possible shapes. So remember this, when we consider different functional forms, the models are like this. Now, if we are considering a simple linear regression model, what is the slope? The slope is simple linear regression model is beta 2. What is elasticity? It is beta 2 into delta y by delta x. Delta y by delta x, elasticity. Beta 2 into delta y by delta x. Slope is beta 2. Now suppose that you are estimating a function like this. Y is equal to beta 1 plus beta 2x plus u. Suppose this is quantity and this is demand. You will get an estimate of the slope only. And the elasticity formula is delta q by q or delta q by delta p into p by q. In our formulation it is delta y by delta p, so delta y by delta x into x by y, as you can see. Now, if you are estimating a linear equation, then slope can be calculated as beta 2 into x by y. X is price by q. Beta 2 into not delta y by beta 2 into x by u. Because beta 2 is delta y by delta x into x by u. Now, if you are estimating a linear equation, you can calculate what elasticity by giving values to x and y. But the problem is which x and which y. Now, a solution is you take average x and average y. That will give you an estimate of the average elasticity, beta 2 into p bar q bar. Average price, average quantity. Because we will not have a single elasticity. Elasticity vary from one point to another point on a straight line demand curve. That is the problem. The problem can be solved if you use the log-log model. So remember these points always. Elasticity and slope for different types of models. Now with this, our discussion of simple linear regression model is complete. And remember this, to get a better grasp of simple linear regression model, you go through various examples given as demonstrations in various books of econometrics. You read the examples, go through the interpretations given for various examples, and as we will see later, for performing these models, we will use computer softwares. Without softwares, we cannot estimate regression models because it is time consuming. A lot of softwares are available. There is a free software, Gretel. EViews is there. Stata is there. Then SPSS, Minitab. So many softwares are available. The choice depends on your taste. Gretel is free, but for these softwares you have to pay. If you are interested in programming, R is the best software. And how to use softwares, we will discuss this issue later in a future class.